Significance test for R. The formula for a significance test of Pearson's correlation is shown here. Again, n refers to the number of pairs of scores. This t-value will always be the same as the one obtained in this test of B, since if the slope is 0, the correlation is 0. Thus, if the regression slope is significantly different from 0, then the correlation coefficient is also significantly different from 0. There are several things to keep in mind when computing the confidence level on ρ, the population value of Pearson's R. The sampling distribution of Pearson's R is skewed. R can be transformed to Fisher's Z prime, which is normal. Z prime can be computed easily or found using a computer program. Z prime has a standard error of 1 divided by the square root of n minus 3. The calculation of the confidence interval involves the following steps. First, convert from R to Z prime. Second, find the standard error of Z prime. We write this as S sub Z prime. Third, compute the confidence interval in terms of Z prime using formula shown. The notation Z sub 0.95 means the value of Z to be used in the 95% confidence interval. It is equal to 1.96. Finally, you convert the interval in terms of Z prime back to Pearson's correlation. You usually do this with a computer program. Here you see an example calculation based on an R of 0.627 and an N of 5. The first step is to convert from R to Z prime. The R of 0.627 is transformed to a Z prime of 0.736. Second, we find the standard error of Z prime. It is equal to 1 divided by the square root of 5 minus 3, which equals 0.707. Third, we compute the confidence interval in terms of Z prime. The Z value of the 95% confidence interval is 1.96. The calculations show that the lower limit of the confidence interval is equal to negative 0.65 and the upper limit is equal to 2.122. Finally, we convert the interval for Z prime back to Pearson's correlation. This can be done with the R to Z prime calculator. We end up with a lower limit of negative 0.57 and an upper limit of 0.97. The interval is so wide because the sample size is so small.